Hi guys, and welcome back to my channel. In this video, I'll be going over the SChO Silver Problem 4, and this was sort of like an inorganic puzzle type of question. It, in my opinion, was one of the more difficult questions on this test just because there was a lot of trivia you kind of had to know in order to be, 100% confident in your answers to this question. But I think you could solve this question just with a little bit of educated guessing and going over it in the end to just make sure your answer sort of made sense. So let's just go over it. Chlorine is a widely used compound. In the following, we will look at some of the reactions of chlorine and its compounds thereof. The following is a large reaction scheme with several steps. If several products are formed, it is the unknown indicated by a letter that reacts further. That's sort of important. All the byproducts are given, but without stoichiometric coefficients. Okay, so now let's just go through this, and basically, without even sort of looking at the the actual questions, let's just go through and sort of figure out what each of the different letters are, right? What each of them correspond to. And this is a question basically centered around chlorine. So all of our A, B, C, D, E, F, G, and H are all going to be some sort of chlorine compounds, right? So let's look at the steps first. Step 1, electrolysis with the formation of two byproducts. One is a strong base, the other is a gas. Okay, so we know that this is electrolysis. What is electrolysis? That's basically when you take ions and you're separating them into their elements, right? So you have, in this case, you have NaCl aqueous. So you have Na plus and Cl minus. And basically, when you're doing electrolysis, you take each of these ions generally and separate them and make them into their elemental form. So you have sodium solid and chlorine gas, right? That's what electrolysis does. Basically, you're applying a voltage, you're doing work, and by doing work, you're sort of reversing the direction of spontaneity. NaCl likes to be together, right? They're attracted to each other. Sodium likes to have a positive charge, chlorine likes to have a negative charge. When you do electrolysis, you're basically reversing the direction of spontaneity by applying a voltage, doing work on the system, and forming chlorine gas, right? So our A is going to be chlorine gas, but note that if we had sodium reducing to, or our sodium ion reducing to sodium metal, right, sodium solid, then our net reaction or our net equation would just have sodium solid and chlorine gas, right, as our products. But neither of these byproducts, right, we don't have a strong base and we don't have a byproduct gas. We have our chlorine gas, but remember that's not our byproduct, that is our compound A. So we have a problem, right? That means that maybe sodium was not the thing to reduce, but something else was the thing to reduce, right? And note that this is in an aqueous solution, so there's water basically all around. And another thing to note is that sodium ion, right, Na plus really does not like to reduce, right? That's because sodium's really happy with the plus charge. It has its octet, right? It really wants to lose that extra electron because then it has the noble gas configuration. So the ion, sodium ion, cation, is really not going to want to reduce. So what else can there be that reduces, right? Because when chlorine oxidizes, there must be something that reduces to conserve charge. The thing that can reduce is water. This is in an aqueous solution. So if we have water reducing, we end up with water forming hydroxide and hydrogen gas, right? So this is sort of where you see that, okay, if water reduces, we're forming a base, our hydrogen, our hydroxide, we have a base, and we have hydrogen gas, our gaseous byproduct. So from here, we can sort of see that water is the thing that's reducing, chlorine is what's going to oxidize. So our general sort of equation for this step is chlorine, right? Our chlorine is going to react with water and form some, chlorine gas and hydroxide. I'll just erase this. Hydroxide and our hydrogen gas. And I haven't balanced it stoichiometrically yet, and we'll do that later, but I just wanted to show you what the general sort of reaction would be for step 1. So we form our chlorine gas. That's our step 1. Step 2. Now let's look at step 2. This reaction is done with the use of mercury oxide, right, HgO, and one byproduct is formed, which is a silvery liquid. Okay, so there's sort of lots of information here. The product B is an orange gas at room temperature, and the molar mass is 87 grams per mole. Okay, so we have HgO, that's our reagent, that's a reactant in this reaction, and we have chlorine, another reactant, right? And we can see that there's a silvery liquid formed, and automatically you should sort of think that this is going to be just mercury, our Hg. So basically what you can see is that our mercury is reducing from our a +2 oxidation state in HgO to just the liquid mercury, right? So there's a reduction of the mercury, which means that there's an oxidation of our chlorine, right? So in step 2 we have, so let me write this out, we have a reduction from Hg2 plus oxidation to Hg, right? Which means that we also have an oxidation of chlorine. And so this is where I found the molar mass really helpful. I did not know that, what orange gas, I didn't really get any information from that because I didn't have that trivia knowledge. If you did have that trivia knowledge, good for you. You might be able to solve this easier. But what I did is I went through all the, say, since we have an oxidation of chlorine, it's probably going to be some chlorine X, oxygen Y, right? This is what it looks like because we have some oxidation of chlorine, obviously, right? So what does this sort of mean? This means that we can test out different values of X and Y and figure out what gets us our, molar mass of 87 grams per mole. And when Y is 1, so when we have 1 oxygen, right, when Y equals 1, we'll see that X equals, this implies that X equals 2, and it's sort of this perfect match. So Cl2O is what we end up getting for B. If you try out different values for Y, you'll see that we don't get integer coefficients of X, and that doesn't make sense because we need integer coefficients, right? This needs to be a integer amount of chlorines and integer amount of oxygens. So if you try out a bunch of different values, so you have like a table where you say, okay, Y equals 1, what does this imply? Y equals 2, then you'll sort of just see that Y equals 1 is the only thing that makes sense. So B is chlorine, Cl2O. Okay, now let's look at our step 3. Let me just erase this again. With step 3, it says that the reaction happens at 25 degrees Celsius. The product C in solution has a faint yellow color. A byproduct of strong acid is made. So we have the product C is a faint yellow color, and we have that strong acid is made. Step 4, and if we look at step 4 and step 3, you can see that they're both leading to the same product of C, right? So let's just read step 4 as well. It says that this reaction happens at 25 degrees Celsius, and again, the product C has a faint yellow color. So that doesn't really give us any extra information. That's just telling us C has a faint yellow color. And again, this is trivia. You might know or you might not know. If you did know this, I did not know this when I was doing this problem, but chlorine water, right? When we look at chlorine water, it has a faint yellow color. Chlorine water has a faint yellow color. And why is this, right? Why is this? This is because of the presence of hypochlorous acid, HClO. So when we have chlorine water, basically the chlorine reacts with the water to form this hypochlorous acid, and this is what gives the water a faint yellow color. So you might have not known this trivia, you might have not known this trivia. Otherwise, you can sort of guess HClO or something of that sort. So let's write HClO for C and see how we might be able to deduce this without knowing that, right? So we're also given that in step 3, we have a byproduct of a strong acid, and step 4, we don't have a byproduct of a strong acid. Okay, so that's kind of important, right? We know that with one reagent, we have a strong acid byproduct, with another we don't. So let's see if that gives us any useful information. And the second thing we know is that there's no sort of reagent in this step, right? There's nothing that's reacting with the chlorine except for what is reacting with the chlorine. This was all in an aqueous solution. Like, let's remember that, right? This is all like in water. So, and what we can have present is water. We can have water be reacting with the chlorine. So let's see how chlorine and water can react to form a strong acid and something else, right? If we have Cl2 plus H2O, we can react this and see that this forms, if we have HCl and HClO. So this forms, right, a strong acid and our hypochlorous acid, and you can see that we have 2 chlorines on both sides, and we have balanced oxygens and hydrogens on both sides. You can, and say with the second reaction, with step 4, right, if we have Cl2O and we reacted that with water, you can see that this just forms 2HClO, right? So we have 2 oxygens on both sides, 2 hydrogens, and 2 chlorines. So there's no byproduct of strong acid. So here we have a byproduct of strong acid, and here we have no strong acid byproduct. So I think this step was a little bit tricky just because, or to me it was a little bit tricky because I did not know the faint yellow color, and so I sort of guessed that it would be HClO, looked at the equations that would work, because if we look at this entire scheme as a whole, right, we can see that every single reaction we're oxidizing the chlorine a little bit. So if we think about our end products, right, at least so far, we've just been oxidizing the chlorines a little bit. So if we look at our end products are probably going to end up being some perchlorate or something like this, because this is the highest oxidation state a chlorine can have. +7 is the highest oxidation state it can have because it's a halogen. It can only lose 7 electrons, right, before you have to start taking electrons from its noble gas core, right? So we're probably going to end with something like perchlorate. And so you don't want to oxidize it all the way, right away. So if we want something that, you know, has a higher sort of has a decently high oxidation state, right? From chlorine gas, we go from a 0 oxidation state to a +1 oxidation state with HClO. So you want to gradually oxidize this, but you don't want to have the oxidation state be really high, and because then the scheme would probably just end there. So that's sort of why I reasoned and guessed HClO. It's sort of like a middle ground thing. So that's one way you can approach and guess that is the product. But this definitely was a trickier step, and it's one you probably have to come back to make sure that you got the right answer. Let's look at step 5, right? Step 5, it says this reaction happens at 75 degrees Celsius. The product D's cation oxidation number is +5. So this is where I sort of, this one was a little bit easier because it tells you that your chlorine oxidation number is +5. So what does that mean? What can have a +5 oxidation number? You might know ClO3 minus, right? And if we look at this, that chlorine in ClO3 minus has a +5 oxidation state. And this is a really, really common anion, right? ClO4 minus and ClO3 minus are very common anions. And so with a +5 oxidation state, that sort of matches up with step 5. So you can guess that step 5 is just going from HClO to HClO3, right? Because we don't have any other counter ion except for a hydrogen ion, so we can just guess that HClO is going to HClO3. Now let's look at step 6. So basically with step 5, the key information was that the oxidation number is +5, right? And you should sort of automatically know that, okay, it's most likely going to be my ClO3 minus anion. This is because it's a very, very, very common anion, right? A very common chlorine anion. Next step, step 6, we have a strong acid being used as a catalyst. The product H is highly explosive and the molar mass is 67.5 grams per mole. There was a typo in this question. It said 100 grams per mole previously, but the actual answer is 67.5 grams per mole. This one, again, was a little bit difficult, so I wouldn't do this right away. I would go to step 7, but if you knew this, you could see that with step 6, it told you that your product is highly explosive, so this might give you some indication of what the answer is. And you also do have the molar mass, so if you had the molar mass and you knew that it's highly explosive, so what you can do is you can go through again like how we did before, ClXOY, right? You can be like, okay, y equals 1, what happens? Y equals 2, what happens? Etc., right? And you'll end up getting that you have ClO2. So you'll have x equals 1, y equals 2. And with this combination, you'll get this molar mass. And so the answer is H is ClO2. So with the molar mass questions, I would just do this sort of systematic way because you know it's going to have chlorine, you know it's going to have oxygen, right? This is oxidation of chlorine. This is going to be oxo compounds of chlorine, right? So you're going to have some amount of chlorine, some amount of oxygens, go through all the combinations, and pick one where you have the molar mass working out with the given molar mass, right? And eventually you'll get ClO2, and ClO2 is actually a radical, right? If you look at the number of valence electrons, chlorine has 7 valence electrons, oxygen has 6, so you'll have 12 plus 7 valence electrons, 19 valence electrons, which means that because there's an odd number, right? The odd number, we have 1 electron is going to be unpaired, which means that we have a radical. So ClO2 is a radical, right? And remember, radicals are very, very unstable. Electrons don't like to be unpaired. They like to be paired together, right? And so when we have radicals, they're really, really unstable. And that's why this is so explosive, right? It's going to do anything it can to react with anything that's around it, right? For it to basically for it to become stable and lose the fact that it's a radical, right? It wants to go from a radical and pair that electron. So because of this, it's very, very unstable. So that is why we have it being highly explosive. And for H, that's why we end up with ClO2. Now let's go to step 7. We see that barium nitrate is used. The product E is a white precipitate. The byproduct is a strong acid. Okay, so this one isn't very difficult at all. We have HClO3, which is a strong acid, remember that. And we have barium nitrate mixed in. So this is classic double replacement reaction. Double replacement. So what happens is the cation-anion pairs are just going to switch. So you're going to end up with barium ClO3, BaClO3, right? And you're going to end up with HNO3. Sorry, this is going to be BaClO3 2 because we need to match the charges, right? Barium has a 2+ charge, ClO3 has a minus charge. So there needs to be 2 ClO3s to equal 1 of the bariums. And so this is the products we form, right? We're just switching the anion-cation pairs. That's a classic double replacement reaction. And we can see that our barium chlorate this is going to be a solid. It's going to be our precipitate. And our HNO3 is going to be aqueous, and we know that nitric acid is a strong acid. So strong acid byproduct. So we can see that we sort of checked all the boxes off. And you might have known that BaClO3 is a white precipitate. You might not have known that, but either way, it's not easy to figure that. I mean, it's not difficult to figure that out because this is just a normal double replacement reaction. So at the end of the day, we have E being BaClO3, 2, right? And now let's look at step 8. If the solution from step 7 is heated slightly, a new white precipitate forms, F plus G. So we have two sort of compounds that are forming. The molar mass of F is 208 grams per mole, and molar mass of G is 336 grams per mole. And again, this is sort of, you want to do that sort of molar mass check that we've been doing before. Let's go through the actual questions first because there's some important information here. So let's look at X.1. Identify A and write the reaction equation for reaction 1. With A, if we remember that, we got Cl2, and our reaction equation it's written here, but I didn't balance it, so let's just balance it now. We want to balance the chlorine, so we need 2Cl- on the left side, 2Cl- plus H2O, plus 2H2O actually, goes to form Cl2, so we balance the chlorines, goes to form our hydroxide 2OH-, right, because we want to balance the oxygens, and we want to balance the hydrogens, so we need hydrogen gas, right, because we have 4 hydrogens on both sides. And you can see that we have equal charges on both sides. We have -2 charge on the left, -2 charge on the right, so charge is conserved. That's good. This is our reaction equation. Next question, X.2, identify B and the silvery liquid byproduct. So B was Cl2O, and our liquid byproduct was this was Hg, was our byproduct. So next, X.3 is just looking at everything, and the information I wanted to just go over was that E, F, and G all contain the same cation. So if we look back up, right, E has our barium cation, which means F and G are also going to have our barium cation. So we need to account for that in our molar mass. Another way to think about this, right, is if we have BaClO3 and we're heating this and we're forming 2 products, this is sort of like going to be an oxidation and reduction of chlorine at the same time. This is kind of what happens if when hydrogen peroxide decomposes into water and oxygen gas, right? This is a common form of this sort of reaction. We have oxygen reducing to form water, right? Oxygen is reducing to form water. Oxygen is also oxidizing to form oxygen gas. So we have these sort of 2 reduction and oxidation of the same element going on. And that happens in certain cases where you have sort of one reagent and it's has an element that's oxidizing and reducing at the same time, right? Some of it is oxidizing, some of it is reducing. Because remember that oxidation and reduction have to come together, right? They can't happen separately. So this sort of thing is happening with our barium BaClO3 too, right? So we're going to have chlorine being the thing that's oxidizing and reducing. In this case, chlorine is going to reduce in one, and chlorine is going to oxidize in the other. The only way for chlorine to oxidize, right? Chlorine has gone to is a +5 oxidation state right now, if we remember that from D. So it can only go to +6 and +7. +7 is very, very common. That's our perchlorate anion, ClO4-. And remember we said that, okay, that's sort of our final stop, right? Perchlorate is going to be our final stop. That's the highest oxidation of chlorine. And if we see that F and G is our final stop. So in the synthesis. So what we're going to assume, what we're going to guess, is that one of these that is formed is BaClO4 2, right? Our chlorate is going to be formed, or our perchlorate compound is going to be formed. That's our guess, and we can check this, right? We can check this with our molar masses, and we'll see that this works. The molar mass of G is 336 grams per mole, and barium perchlorate is also 336 grams per mole. So G is, this is what G is, basically. So the next part is finding out what F is, and with F, we know that there has to be a reduction of chlorine, right? So we know it's going to be ClO something, but the O either has to be less than 3 or it's 0, right? And if you check this with the molar masses, if you look at the molar mass is 208 grams per mole, you'll pretty easily see that this has to be BaCl2. So how you can set this up is you can be like, okay, ClOx maybe 2, right? That's going to be our compound, and X is going to be less than 3, and you know what the molar mass of this is, and you'll find that X equals 0. So this implies that our compound is BaCl2. So we'll end up with F and G being, F is going to be our BaCl2, and G is going to be our BaClO4 2. Okay, so now we've gone through this entire synthesis and we know all the compounds. So hopefully this sort of made sense how we went through it. It's a little bit difficult because there is some trivia you just need to be aware of, especially with common elements like chlorine, nitrogen, halogens, nitrogen oxidations, sulfur sort of things. These like sort of common main group elements, you have to know a little bit about their compounds, right? Know about their oxygen compounds. So it's useful to just go through some sort of cheat sheets where they have a bunch of information about the oxygen compounds of these elements, because it just helps you get more aware of the different compounds, and you don't have to decode as much if you have some previous knowledge, right? But you can see that this was doable if you used some reasoning skills and a little bit of educated guessing. So now let's go to the last part of this question. So we've solved for all C, D, E, F, and G, and H. So just to go through all of it, C is our HClO, D is our HClO3, H is our ClO2, E is our BaClO3 2, G is our barium perchlorate, and F is BaCl2. So we have all of our compounds now, and we can go and look at our last question. Complete and balance the following reaction equations. So this is not difficult because we've just solved for AB all of the compounds. So we just have to do mass balance at this point, which is pretty easy. So if we look at A is Cl2 plus H2O, right? We're just writing this equation, and we actually wrote this above because I used this equation when trying to figure out the answer for C, right? But you technically didn't need to know this equation until x.4, until this last part, and but we did write this above, so I'm just going to copy it. Cl2 plus H2O goes to HCl plus HClO. So that's what this question is saying. Cl2 plus H2O goes to HClO and HCl. That's our first reaction. Next, we have C going to D plus HCl. C was HClO, D is HClO3, so let's write this. C is HClO, goes to HClO3 plus HCl. And this just comes down to balancing stuff. So first we want to balance our oxygens, right? We have 1 oxygen here, 3 oxygens here. Let's put a 3 in front here to balance our oxygens. Next, we want to balance our chlorines, right? So we have, let's balance our chlorines. So we have 3 chlorines. 1, 2 chlorines on this side. So if we want to balance our hydrogens and chlorines together, which is not too difficult, we just want to put a 2 here, right? So now we have 3 hydrogens on the right side and 3 hydrogens on the left side, and we have 3 chlorines on both sides. So that should have been, decently simple. The next part is E goes to F plus G. Remember that E is our BaClO3 2 and F plus G, so let's just write this out. BaClO3 2 goes to BaCl2 plus BaClO4 2. Okay, so first we want to balance I thought it was useful to balance our oxygens, right? So we have 6 on oxygens on here, we have 8 oxygens here. So we want to find sort of a common multiple. So if we have 4 here and 3 here as our coefficients, you can see that we balance our oxygens, right? We found this common multiple of 24. So with those coefficients, we balance our oxygens. And you'll actually, now you might say, okay, let's go balance our other elements, but you'll see that this is already balanced. We have 4 bariums here, 1 plus 3 bariums, so we have 4 bariums on the right and left side. We have 8 chlorines on the right and left side. We have 8 chlorines here. 8 chlorines here, 2 chlorines, 6 chlorines. So we have 8 on both sides, and we've already balanced the oxygens. So this is a perfectly good equation. And so this is our final answer for the last part of this question. And these 3 equations this is our answers for x.4. Okay, cool. So that should have been pretty sort of self-explanatory. I didn't think that was too difficult. You just had to, once you knew the compounds, it's just balancing the atoms on both sides, which isn't super difficult. Okay, cool. I hope this was informative to you. I know this was a little bit of a trivia question, but I hope some of the ways I tried to talk through and explain how you think about these things, especially when you're given stuff like molar mass, when you're given stuff like, what precipitate, when you're given that HGO is, forming a silvery liquid, and you can sort of guess that that's just going to be Hg. All these sort of little things, you might not know that one gas is orange and one gas is yellow and one, this thing in solution is green, but hopefully you're able to put together the little information you do actually know and solve the question even without knowing all this sort of trivia, right? So I hope that this video gave you an idea of how to, even when you don't know everything, to sort of guess and make educated guesses and go back and sort of check that your educated guesses make sense. Okay, thank you guys so much for watching. I hope this was informative, and I'll see you guys in the next one.